We continue with Gauss's law with an example that is similar to one we've done previously, but let's go ahead and we'll kind of go through this one quickly if we can. Based on the figure, determine the charge on all surfaces, the E field magnitude at all points, and graph the results. Once again, we have essentially a cannonball here, and then on the outside of it, we have a basketball with a thick metal shell, and the net charge on the inner surface of this metal basketball, we're told, is positive 3Q, and on the outer surface, the charge is positive 2Q. What does that mean? That must mean that the charge on the exterior surface of the cannonball has to be exactly opposite to this positive 3Q here. So that's got to be negative 3Q. So let's find the electric field magnitude at various points. For R less than RA, that is on the inside of this cannonball, the electric field magnitude is 0. Similarly, why don't we skip ahead to between RB and RC. Between RB and RC, the electric field magnitude is also 0. On the interior of any conductor in electrostatic equilibrium, the electric field is 0. What about between RA and RB? That is, if we were to draw a Gaussian surface right there of radius r. Well, let's use Gauss's law. Q enclosed over epsilon naught is equal to the surface integral of E dot dA. What's the total charge that's enclosed here? It has a magnitude of 3Q. The electric field magnitude is constant at each point, so we can integrate dA, and when we have a sphere and we integrate dA, we get A, which is 4 pi r squared. So the electric field has the magnitude of 3Q over 4 pi epsilon naught r squared. Now, that was a negative Q. So that means that the electric field lines in here are pointing towards this cannonball, because electric field lines point away from positive charges and toward negative charges. So that might come into play here whenever we draw our graph. All right, what about beyond RC? That's the last section that we need to deal with. So what about R greater than RC? Q enclosed over epsilon naught equals the integral of E dot dA. What's the total charge that's enclosed here? The total charge that's enclosed is plus 2Q. I'll go ahead and circle that. This one has minus 3Q. This one has plus 3Q. Those cancel each other out. So the net charge that's enclosed when we're on the outside is positive 2Q. And this is a Gaussian sphere that goes all the way around here, where our R value is bigger than RC. The numerator here is going to turn into 2Q. This is positive 2Q. The electric field magnitude is equal, so we're going to integrate dA. When we integrate dA, we get A, which is 4 pi little r squared. And so the electric field is going to have what magnitude? 2Q divided by 4 pi epsilon naught r squared. If we wanted to simplify that, we could. There you go. And these electric field lines point outward. Up here in this top diagram, can we see it? Yep, we can barely see it. At the top of the screen there in the upper right, those field lines are pointing in that direction. On the outside, because the net charge on the inside is positive, those field lines point in the other direction. So when we graph this, it's probably appropriate to graph it something like this. There's R, Here's our electric field, with this being positive electric field, that being negative. And we want to label here, there's RA, there's RB, there's RC, RA, RB, RC. Let's start with the easy ones. R less than RA, the electric field is 0. Between RB and RC, the electric field is 0. Between RA and RB, we have the electric field proportional to R squared, but that has a different direction than the electric field down here. So maybe we should call one of them positive and one of them negative. So maybe we should do something like that right there. And when we're beyond RC, maybe we should do something like that, where both of those, E is proportional to 1 over R squared right there. And same thing here, E is proportional to 1 over R squared. And E is equal to 0 there and there.